What if our electronics could communicate using the same chemical signals our cells use? This would offer many benefits, such as transmitting signals to places where electromagnetic waves can't reach or might be too disruptive. The answer to this question is molecular communication, an emerging field synthesizing nanotechnology, engineering, and synthetic biology. Most have heard of the Internet of Bio-Nano Things, a theorized system of interfaces and tools inside humans and their environment that enable communication and interaction between human biology and technological systems. The backbone of this concept is molecular communication, or MC. MC has become a focal point for medical science recently, with numerous papers discussing and testing new techniques for targeted drug delivery and health monitoring. Today we'll look at these applications and some other less discussed near-future uses. In traditional electronics, signals carried by wires or on waves in the air can be likened to radio signals. They are transmitted and received in real time, and have a fixed amount of bandwidth dependent on the frequency of the signal. MC is more like a text message than a radio signal in this analogy. Each packet of data sent via MC is represented by a molecule containing a wealth of information. If the receiver is designed to accept many different molecular signals at once, the throughput of such a system can compete with or surpass traditional digital communications. Modern computers talk to each other using binary, a simple on and off state in the absence or presence of electrical charge, while MC can have a variety of states encoded on a single molecule. The way molecules move and interact at nanoscales offers even more complex types of data. Microtubules are mobile and can be circulated in cellular and intracellular fluids without losing their capabilities. The same molecule will interact with a microtubule and a kinesin in different ways, allowing complex interactions from simple molecules. In a process called bacteria-assisted propagation, bacterial cells can accommodate the movement and transformation of other entities such as phages and microorganisms. Thus, bacteria can be used to amplify and convert signals. Cells exchange ions and small molecules through adjacent tissues called gap junctions. Thus, cells can be engineered to only transmit information in the presence of other cells with symbiosis. This allows chemicals to be stored safely inside of cells for long-term use in environments that would otherwise destroy or degrade them. We all remember from chemistry class that the rate of flow in a liquid can manipulate the degree of chemical interactions in a solution. This happens non-linearly, since molecules moving past each other at different speeds will interact in very different ways. Doubling speed does not necessarily double the rate of chemical reaction, and this is especially true in biological cells. These functions are just the surface of what we know to be possible today. More complex interactions, like neurochemical propagation, can blend electrical and chemical energy to transmit data at higher and higher resolutions. Nanomaterials, inorganic structures with specific engineered properties, can diffuse chemicals as well. As these concepts move from theory to application, we have realized electromagnetic waves are not ideal carriers of information in certain environments. Inside the human body, EM might disrupt cells and is impeded by dense tissues. In atmospheric environments, the distances are too large for reliable use of EM. In some industrial settings, EM interference must be avoided, and in others, the design of electronic hardware will block EM waves. We should also recognize that MC not only permits data transmission but energy transmission as well, though in a way very different than we are used to. Consider a bacteria like E. coli with its spinning flagellum tail. The bacteria is dormant until they are exposed to a chemical that activates their flagellum, giving them energy needed to perform different tasks. We can use bacteria like E. coli and activate them in an MC system using specific chemicals, giving us mechanical energy on demand. In one experiment, a receiver and transmitter exchanged signals across a fluid using a combination of proteins, enzymes, kinesins, and microtubules. Two similar kinesin scaffolds attached to a protein acted as a receiver and transmitter. ATP enzymes moved across the scaffolding, carrying chemical signals onto microtubules that flowed freely throughout the solution. These microtubules diffused towards the receiver scaffold, and their ATP enzymes migrated onto the corresponding kinesin, eventually ending up depositing their signal in the receiver protein. Having a medium to transmit high-resolution digital data and energy potential without electrical signals offers a new paradigm in high-tech manufacturing. Imagine a factory that generates no EM pollution by using a network of vein-like channels pressurized with a liquid not unlike the blood inside a human body. Instead of complex isolated wiring circuits, the factory uses one centralized bloodstream, just like a living organism. Throughout the factory, molecules are introduced into the liquid that describe the state of different components and their need for raw materials. The fluid shunts around the system until a molecular detector on a related piece of machinery reads the signal and sends more material where it's needed. At various points throughout the system, unwanted molecules are denatured by heating or introducing chemicals into the stream, preventing unwanted signal lag or feedback loops. Molecules with long-term assignments are designed to withstand higher temperatures, allowing them to continue relaying signals. In lieu of microprocessor controllers, signals are encoded using natural bacteria, engineered biological tissues, and chemical reactions. Unlike electrical signals, molecules can be stored and offer redundancy in case of events like power loss. Instead of consuming large amounts of high-voltage power, this system runs on common organic compounds and water. The thousands of kilometers of wiring strung around modern factories and harnesses are removed, with electricity only being used by machines that perform labor-intensive tasks. For other less demanding tasks, chemical catalysts are circulated in the liquid to provide energy. Hydraulic pressure can also be used to manipulate data while providing mechanical energy as well. Potential medical uses are already in grasp and include near-term applications in preventative care and intervention. Studies show MC touts improved drug uptake and reduced side effects compared to other drug delivery methods, making it ideal for treating cancer and immune disorders. In medicine, we can use MC to gather data on the location of drugs inside the body, as well as using the same data to react to conditions in real time. Imagine a situation where nanomachines are deployed in the bloodstream and need to communicate with each other as they navigate and attack tumors. These machines deploy organic molecules to communicate without harming the host, and these chemicals can be sampled externally to obtain diagnostic information on what the machines are doing and what kinds of problems they are encountering. Further, the nanomachines can directly trigger immune system responses once they have determined which will be the most effective. Specific proteins can be delivered for activating the immune system and/or triggering drug delivery systems in small specific areas without affecting the rest of the body. In addition, real-time monitoring of biological parameters during the execution of these innovative techniques can be integrated by an information exchange with the outer world. We can see this kind of technology is a precursor to a system that might one day supplant the natural immune system and provide added resilience against aging-related diseases. Molecular communication is still in its infancy, but as it emerges on the horizon, it promises numerous disruptive applications. For now, experiments have proven that MC can be paired with traditional processing devices and rudimentary coding languages such as Java, proving they work and are scalable. Most of the challenges found at this phase revolve around working with extant biological structures and processes, but being able to engineer nanomaterials with unique reactions promises to unlock much more utility. To be clear, nanomaterial refers to artificial materials made by man, while nature produces its own nanoscale structures across biology. Something else to consider is that MC technology lacks the security of traditional computing methods, since any adversary with a good understanding of biochemistry can potentially exploit these systems. In medical applications, this is irrelevant, but in industrial settings, it is unfortunately a real concern. IMC is yet another fascinating example, showing how multidisciplinary science has begun to dominate emergent fields. Just as artificial intelligence is a synthesis of neuroscience and computing, IMC combines natural and synthetic biology with engineering sciences to produce a profoundly paradigm-shifting technology with broad applications we have yet to fully grasp. Thanks for tuning in, everyone. I hope you found today's discussion interesting. As usual, like and subscribe, do all that YouTube stuff, it really helps me grow the channel, and have a good night.